of our nice conference. It's a pleasure for me to introduce the next speaker, Professor Dominique Leguillon from the CNRS, French National Center for Scientific Research, and Sorbonne University in Paris, where he works for his entire career. He received the prize for the French Academy of Science in 1994. His main research areas are homogenization theory, singularity theory, and brittle fracture. He taught the finite element method in Paris University, homogenization in Paris and Bordeaux universities, and finally fracture mechanics again in Paris. He wrote a book dedicated to singularities, authored and co-authored 120 papers in international journals. What I would like to say at the end, everybody knows the finite fracture mechanics theory, and it's one of his main contributions in fracture mechanics. Professor Leguillon, please, the floor is yours.
Okay, thank you very much, Mr. Chairman. I will present today the concepts of finite fracture mechanics and application to different situations of brittle materials. This is really dedicated to brittle materials, and I like, before starting, to cite this sentence of Zvi Ashin. It is extracted from the introduction of his paper in 1996, and it's a good definition for finite fracture mechanics. Spontaneous crack formation implies that new cracks appear in a very short time, and it is not possible or of interest to follow the history of their development, okay? So it means that we are interested to a state before the onset of cracks, we are interested after the onset of cracks, but really how it develops in between is something that is very rapid, and we are not really, in this case, interested in description of the details of what occurs in between the two states. Here, I've just drawn a map of the contribution of different contribution to finite fracture mechanics. It is mainly dedicated to the coupled criterion, but here, for instance, I have added two spots that are dedicated to a slightly different theory of finite fracture mechanics called the theory of critical distance of David Taylor, and I know it's also used in Torino here, but unfortunately I try to not offend anyone by forgetting him, but probably I forget some spots. So I apologize for that. Here, I would like to mention two actions. The first one here is the Technical Committee 16, okay? It's chaired by Zoe Yosibash, and it is dedicated to finite fracture mechanics, and I thank Zohar and Leslie Bankshill for having contributed to the creation of this committee. Another mention is the International Training Network. It's a consortium that is part of Marie Curie Actions of the European Union, and it is chaired by Vlado Mantic in Seville. I have also to thank two close collaborators, Eric Martin in Bordeaux, Aurélien Doitrand in Lyon. You can ask questions to him, he's here. And of course, all my PhD students that have worked in this domain since the beginning of 2000. Okay, a little of history. We start, of course, with linear elastic fracture mechanics that deals with the crack growth, okay? You need to have an existing crack, and you study the ability of this crack to grow or not, but nothing is said in this theory about crack nucleation. Here, just to cite three famous names involved in crack growth: Inglis, Griffiths, Irwin, everybody knows this name. And what is the specificity of this theory is that it involves a single parameter, generally called GC, the fracture energy, or equivalently it is a toughness, KNC. At the same, in the 50s, okay, another idea appears is that we could use two parameters, because of course using experiments very often failure is characterized by a critical tensile stress called the tensile strength, sigma c. And using these two parameters allowed to calibrate a length. Irwin did that, of course. Instead of sigma c, he used sigma yield, and used that to define the size of the plastic zone. I can mention also McClintock and Novosilov and Severin, more dedicated to the crack, a kind of crack increment length here. And of course, once you have done that for a crack tip, you can extend to the root of a V-notch. You know, the singularity is just slightly different, but the same approach can be used. I have to mention also the works on the role of the generalized stress intensity factor. I mean the intensity factors that are involved in the Williams expansion in all cases, not only the crack, but even V-notch. And can mention the work of Alberto Carpinteri here. And this very important experimental work by Dunn and his group, probably they show that the generalized stress intensity factor is the appropriate parameter to predict crack initiation at a V-notch. It is an experimental work, but it is very important because they show that the generalized stress intensity factor is the right parameter to be used. Now we can move to finite fracture mechanics in the 90s, at the beginning of 2000. John Nairn in 93, Zviashin 96, and here I mentioned also the theory of critical distance of David Taylor, but we mustn't forget Tony Kelly's group, who did finally in the 70s, who did finite fracture mechanics, but without using the name. But there are very interesting results of this group obtained in the 70s. Then finally, the couple criterion. I contribute in 2002, and I recommend the review paper by Philip Weisgraber in 2016. And as I will show, we have had successful applications to a wide range of situations. Okay. What is the other approach that can compete with the coupled criterion? There are cohesive zone models and phase field method. But these, from my point of view, these approaches are more numerically dedicated than having a physical basis. Okay, now what is the idea for finite fracture mechanics? Here I mentioned the work of a group, Parvizi, Garrett, and Bailey, who was a member of the group of Tony Kelly's, and did these experiments. They make a tensile test on the cross-ply laminates. You know, you have a middle layer like that with fiber at 90 degrees. It means orthogonal to the tension, to the loading direction, and the two outer layers are called zero because the fibers are aligned with the loading force here. And what do they obtain is something like that. This is the applied strain when appears the first transverse crack in the middle layer here. And they obtain something like that, and what is to be retained here is this dramatic increase in the applied strain when the inner layer becomes very small. But at that time, it has been a very big controversy because many people claimed that this is a Weibull effect. And finally, Tony Kelly in 1988 wrote a paper to show that it cannot be only Weibull. Okay, Weibull theory can explain some parts of the increase, but not completely. This is a work in 1988. So what they do, they measures and they suggest that it is an energy condition that can explain the dramatic increase. It means that when the inner layer becomes thinner and thinner, there is not enough energy available to create a crack. And then you have to increase the load to increase the available energy and then apply an energy condition to create a crack. And what we suggest, finally, is to add to this energy condition another condition that is a stress condition. It means that if you have a thick ply, okay, for instance 3 millimeters, you start loading, then here you have fulfilled the energy condition, but you have still to load up to this line in order to fulfill the stress condition. On the contrary, if it is a very thin layer, then you load, you reach the stress condition here, but you have still to increase the load in order to have enough available energy to create the crack. This is the idea for starting the couple criterion, and this kind of curve with a plateau like that and then an increase is met in many cases. These are experiments by Andersons on submicron films. It was silicon nitride deposited on a compliant matrix, and they examine multi-cracking of this thin layer, and again they have a plateau here and then an increase. The error bars are the experiments, and the red line is the proposed prediction by the coupled criterion. Okay, now I try to come back to a standard test. This standard test is bending of a notched specimen like this one. Okay, if I do some finite element calculation, if I use a stress condition, if the notch is sharp, everybody knows that here in the vicinity the stress tends to infinity, and then it means that it is bigger than any threshold. So if you decide to use a stress criterion, you can predict onset whatever the applied load, even very small. On the other end, if you consider an energy condition, except if omega is 0, I mean if the V notch is open, then G, Griffith's energy release rate, is 0 at the corner. So no onset can occur. If you use this criterion, you can conclude that no onset will occur. Of course, the conclusions are contradictory, and one can imagine that something else appears. It means failure occurs, but for a finite applied load. So we have to try to explain this. And how to state this criterion to predict crack onset? A simple one, a macroscopic one, using as few parameters as possible to predict the crack onset. The starting point is a very simple energy balance, the one used by Griffith, okay? This is the change in potential energy between two states, before the initiation of a crack and after the onset of a crack, the change in kinetic energy and the energy consumed by the crack growth. Here it's a 2D model, and you have to understand, of course, this equation per unit thickness. Otherwise you have to add the thickness of the specimen here. Okay? In quasi-static tests, the kinetic energy is 0 before failure, so this term is necessarily positive, and from that we derive this inequality. But you see that this inequality is rather a rough inequality, because sometimes the change in kinetic energy can be large. Okay, So the coupled criterion states that two conditions must be fulfilled simultaneously. First, there is enough energy available to create a crack of length A, and the tensile stress is greater than the tensile strength all along the supposed crack path. It means between the 0 and A. The A is the crack length observed after the initiation. It is a non-local condition. And as a consequence, it's not an assumption, a consequence of these two conditions is that the nucleation occurs in general abruptly. In general because it accepts the crack growth, but as soon as the V-notch is open, you have an abrupt initiation of the crack jumps, okay? So, if we try to summarize, this is the condition, the energy condition, and this is the stress condition. In general, sigma of Z here is a decreasing function, okay? When you are approaching the singular point or stress riser, sigma is big and it is decreasing with the distance. So this can be equivalent to this condition. But remember that it is not a point stress criterion, it is simply the consequence of this condition. Okay, how to implement the coupled criterion? Okay, we have computed once for all the stress field before the onset of a crack in order to check if the tensile stress is bigger than sigma C or not. And then we release pair of nodes along the supposed crack path to calculate the potential energy at this state. It's possible doing this releasing pair of nodes after pair of nodes to construct this function, this potential energy as a function of the crack length, and then this term G incremental of A, and okay, and we can also in the same way calculate G of Griffiths, the energy release rate. Okay, so remember, and it's very convenient to use dimensionless parameters. Here, this is the conditions for crack nucleation, and this is the condition for crack growth. Okay, how does it work? Let us consider here, this is typically what, unfortunately, the stress condition is very light. Okay, this is 80% of the failure force. The stress condition is here. It's a very light gray line, and the energy condition is here. From here to here, you see that the stress condition is fulfilled, but the energy condition is fulfilled somewhere far on the right. So there is no match. If we increase the load, unfortunately, the gray color is not a good choice. It is here up to here, and you see that the stress condition is fulfilled from here to here, the energy from here to the right. The stress condition defines an upper bound of admissible crack length. The energy conditions define a lower bound, and the upper bound is smaller than the lower bound. So there is no match. If we increase again the loads, then at the moment we get this point where the stress condition and the energy conditions are fulfilled. This means that for this load, the crack jumps from here to here. And then we can consider that we can now, there is a crack, we can consider G, and you see that at that point G is bigger than GC. It means that the crack initiates by a jump and then grows in an unstable manner, okay? Another interesting point is, compression on drill specimen. You have a specimen and a hole in the middle, and you put it in compression. This allows to have two stable cracks. Okay. Here I consider the case where sigma C is small and GC is high. It is typically the case of polymer. As sigma C is small, it is very easy to fulfill the stress condition. Here it is fulfilled almost everywhere in the figure, but you see that the energy goes through a maximum and then decrease. Philip Weisgraber called this situation negative geometry, okay? So, of course, no match between stress and energy. If we increase the load at the moment, we have a point here where the energy condition is fulfilled, and of course the stress condition is also fulfilled. It means that the crack jumps from here to here, and then we can consider now the G, and you see that it's very easy to show that when there is a horizontal tangent here for G incremental, G goes through this point, and G is equal to GC and decreasing. This is a classical arrest criterion. It means that the initiation length is also an arrest length. Next, I will consider the opposite case. Now we have a high sigma C and a low GC. This is for ceramics, for instance. Okay, so now, unfortunately, this stress is the stress condition is here. You see, it's very difficult to fulfill the stress condition because it is just fulfilled here, and this is the energy. If we go on loading, we obtain this situation, but the stress condition is here, and there is still no match. Stress is fulfilled here, energy is fulfilled at that point. So no match, and we increase again the load, and then we obtain again the point where the crack initiates and jump from that point to that point, and we can again consider the G, the energy release rate of Griffiths, and you see that again G is bigger than GC, so you have an unstable crack growth up to at least that point, that is G equal to GC and decreasing. It's an arrest length criterion, but you see that here there is an excess of energy, and depending on the situation, this excess of energy can also be computed to increase the crack. And finally, if the excess of energy here is entirely consumed by the crack growth, it cannot go beyond that point. It means that we have a lower bound for arrest length and an upper bound for arrest length with these two. I must mention that in general, it is a lower bound that works. It is the standard arrest criterion that works, but we know some cases where the crack goes a little further, somewhere in between these two bounds. This is the case of laminated ceramics with residual stresses. Okay, so few words about another approach that allows to have quasi-analytical expression of the criterion. We use Williams expansion here, and we use also match asymptotic expansion procedure in order to derive this relation. This is the Williams expansion. For people who know match asymptotic expansion, this is the first term of the inner behavior of the first term of the outer expansion. Okay. And G incremental in this case can be derived explicitly. There is a scaling coefficient A that can be computed once for all for a given omega. And this is the square of the load here, and the crack length at the power 2 lambda minus 1. Lambda is a singularity exponent here. Sigma here is just derived applying the constitutive load to the displacement, and you can, in the same way, calculate G. And in this case, the coupled criterion takes this very simple form. We can have an explicit relation for A, for the crack jump here, GC divided by A, the scaling coefficients times sigma C square, and the criterion takes this Ehrenreich form that the generalized stress intensity factor must be larger than K, the critical value Kc, depending on Gc and sigma C. You see that if it is a crack, I mean omega is 0, lambda is 1/2, this term is 1, we have a relationship which involves only Gc, and it is Griffiths. On the other hand, now, if we have a flat edge, okay, there is no longer any stress concentration, no longer any singularity. Lambda is 1, this term is 1, and then we have a relation here, a relationship involving only sigma C. It is a tensile stress condition, okay? And we can extend these results to many different situations. This is an example of the prediction by the couple criterion compared to some experiments by Yossi Bash and co-workers on alumina specimen. You know that in this case it works quite well. It's a comparison between the the critical value of the generalized stress intensity factors. Okay, so now we will try to move to the 3D situation here. 3D situation. The big difficulty when considering 3D is to define correctly the crack shape at nucleation, okay? Because in 2D, okay, the crack extension, it is a straight line. This is an assumption, but not very restrictive. But, okay, it is defined by just a length and a direction, okay? But in 3D, it's by far more complicated because we have to define first a direction and a shape. And the shape, a priori, needs an infinite number of parameters to define exactly the crack front. So we have to add some assumptions in order to implement the couple criterion using 3D. And this assumption is, first, during nucleation phase, the crack is plane. It's almost the same assumption as the crack increment is a straight line, okay? So this is not a big assumption. The second one is bigger. We have to determine the plane in which the crack develop, okay? And up to now, we have used an assumption that is that the plane direction is defined by the maximum tensile stress acting on it, okay? You have a plane, you check many possible directions, and you select the one where the tensile stress is maximum, okay? But now there is an ongoing work with Aurélien Doitrand to replace this condition by something that derives immediately from the couple criterion instead of being an assumption. And the result is not very different of the one obtained by this assumption, but it's more rigorous. And in addition, we have to, now within this plane, it is plane, we have defined the direction of this plane, and we have to give the shape of the crack within this plane, and it is defined by the level lines of the tensile stress in the plane. Once you have selected the plane, you plot the level lines of the tensile stress. And these level lines define the crack shape. Indeed, these are the level lines. Of course, you know, if I select, for instance, that one, or I know that inside this region, the tensile stress is necessarily bigger than the stress that defines this level line here, okay? So this is an example on 4-point bending, bimaterial specimen and aluminum and epoxy. This is, again, a work by Dunn and co-workers here. It's bending. You know, the specimen has been rotated by 45 degrees, and a 4-point bending is applied to this specimen. In this case, we know that the crack developed in the interface. So the first assumption, the crack is plane, is fulfilled. The second assumption, the direction of the plane, is fulfilled. We know it. It is the interface, okay? And in this interface, we plot the level lines of the tensile stress. Level lines of the tensile stress have this shape, and you see that each line can be defined by a single parameter. This is what we were trying to obtain. Each line is defined by a single parameter, the distance from the corner to the to the line. Then we can use the couple criterion and solve the problem. And these are the results Okay, we have to identify these two parameters because they were not given in the work by Labossière and Dunn. But, okay, so with two parameters we can match any curve, but you need anyhow the trend. The trend is fulfilled. Okay, about the asymptotic approach, I will say very few words because even if the way to obtain this expansion is slightly different from the 2D case, the results at the end is exactly the same. Simply, you have to consider the exponent of a 3D singularity. You have to consider this scaling coefficient in a 3D point of view and so on. But otherwise, it is exactly the same as in 2D, provided you have been able to characterize the crack by a single parameter. Okay? The last example I will show you, because it's the crack from segmentation under mode 1+3 loading. Well-known experiments have been carried out by Pham and Ravi Chanda, and this is a picture. What happened is that the crack would like to twist like that, but it's not possible. So facets appear along the crack front, and we will try to predict the onset of these facets and the spacing in between. A lot of work has been done on theoretical point of view by Pons and Karma, for instance, Jean-Baptiste Leblond as well. It was mainly to the next stage. I mean, the facets have been created, they have coalesced, and they are growing. But few is done on the initiation phase, except the work of Ravi and Pham, but it's mainly experimental work. And I can mention also the work by Lazarus and co-workers on this first stage. With Aurélien, we have used match asymptotic expansion, but with respect to the root radius of the notch in order to match with the experiments of Ravi. And I show you what we obtain. First step, we define the crack planes. Okay, it's not very difficult because we have just one direction to check. Okay, we have just one direction to check. We can select the plane here and its direction orthogonal to the maximum tensile stress. Inside this plane, we can plot the level lines of the tensile stress, and you see that these level lines, the shape is very close to that observed in experiments. Okay? Then we can implement the coupled criterion to determine the crack spacing. People who are interested, I can explain how it is done, and these are some results concerning the apparent stress intensity factors at nucleation. Okay, roughly we have obtained that the crack spacing is 5 times the crack tip radius, and the Pham and the Ravi found something like 4 times. Okay, so we were quite in a good agreement. So to conclude, this coupled criterion has been successfully applied in many cases: fiber debonding, delamination, transverse cracking, damage in woven composites, multi-cracking thin films, crack deflection, layer ceramics, residual stresses, oxidized polymer, crushing of a pebble. You know, there are some very different topics, and it works quite well. Of course, the advantage is that it requires only linear calculation instead of the two mentioned approach, phase field and the cohesive model, who have some convergence issues in order to. Okay. Among the extension, I can mention that non-linear behavior, as well, geometrical as well as material non-linear behaviors, dynamic effects here, and also some efforts have been made to have a systematic implementation in some commercial codes, work by G.I. Lee and by Aurélien Doitrand. Thank you.